Question 251. For this question, refer to the TerramEarth case study. You need to implement a reliable, scalable GCP solution for the data warehouse for your company, TerramEarth. Considering the TerramEarth business and technical requirements, what should you do? A. Replace the existing data warehouse with BigQuery. Use table partitioning. B. Replace the existing data warehouse with a compute engine instance with 96 CPUs. C. Replace the existing data warehouse with BigQuery. Use federated data sources. D. Replace the existing data warehouse with a compute engine instance with 96 CPUs. Add an additional compute engine preemptible instance with 32 CPUs. The correct answer is option A. Replace the existing data warehouse with BigQuery. Use table partitioning. Explanation: the primary goal is to implement a reliable, scalable, and cost-effective data warehouse for TerramEarth. Considering their business and technical requirements, the most suitable approach is why BigQuery is the best choice. Massive scalability. TerramEarth generates 9 terabits of telemetry data per day from 20 million vehicles, which requires a highly scalable and managed data warehouse. BigQuery is serverless and highly scalable, capable of handling petabytes of data with minimal operational overhead. Managing this scale of data on compute engine would be inefficient, expensive, and complex. Table partitioning. Table partitioning allows you to organize the data by date, region, or any other logical category. Since TerramEarth collects daily data, 9 terabits per day, using time partition tables based on ingestion time or event time significantly improves query performance. Cost efficiency, by scanning fewer partitions. Data management, automatically expiring older data if needed. Cost effectiveness, BigQuery operates on a pay-per-query model, meaning you only pay for the data scanned during queries. Compared to compute engine, which incurs continuous compute and storage costs, BigQuery is far more cost-efficient. Minimal maintenance. BigQuery is a fully managed data warehouse, eliminating the need for infrastructure management, backups, or scaling configurations. This aligns perfectly with TerramEarth's business requirement for scalability and reliability. Why other options are incorrect? Option B. Incorrect. Compute engine with 96 CPUs does not scale well for massive data processing like 9 terabits per day from 20 million vehicles. Managing infrastructure, scaling, backups, and performance tuning would be complex and costly. It violates the business goal of minimizing operational overhead and maximizing scalability. Option C. Incorrect. BigQuery with federated data sources is not ideal for this scenario. Federated queries allow querying data in cloud storage, cloud SQL, or Bigtable without ingestion, but it does not optimize cost when dealing with high-velocity streaming data. Federated sources have higher latency compared to native BigQuery tables. The requirement specifically mentions replacing the data warehouse, not querying external sources. Option D. Incorrect. Using compute engine with 96 CPUs and adding a preemptible instance is not scalable. Preemptible instances can be terminated at any time, causing interruptions in data processing. Additionally, compute engine lacks built-in query optimization and scalability like BigQuery. This approach increases infrastructure management and does not align with the business goal of scalability and reliability. Question 252. For this question, refer to the TerramEarth case study. A new architecture that writes all incoming data to BigQuery has been introduced. You notice that the data is dirty and want to ensure data quality on an automated daily basis while managing cost. What should you do? A. Set up a streaming cloud data flow job, receiving data by the ingestion process. Clean the data in a cloud data flow pipeline. B. Create a cloud function that reads data from BigQuery and cleans it. Trigger the cloud function from a compute engine instance. C. Create a SQL statement on the data in BigQuery and save it as a view. Run the view daily and save the result to a new table. D. Use Cloud Data Prep and configure the BigQuery tables as the source. Schedule a daily job to clean the data. The correct answer is option D. Use Cloud Data Prep and configure the BigQuery tables as the source. Schedule a daily job to clean the data. The primary objective is to ensure data quality on a daily basis while keeping the operational cost minimal. Given that the data is already landing in BigQuery, the most efficient and automated approach is to use cloud data prep. Why other options are incorrect? Option A is incorrect. Using cloud data flow with a streaming pipeline introduces unnecessary costs since the requirement is for daily batch processing, not real-time data processing. Additionally, deploying data flow requires infrastructure management and maintenance, adding operational overhead. Option B is incorrect. Triggering a cloud function from a compute engine instance is inefficient and costly. Compute engine would remain underutilized for most of the day, resulting in higher infrastructure costs. Moreover, cloud functions are better suited for event-driven tasks, not scheduled batch data cleaning. Option C is incorrect. Creating a SQL view in BigQuery only masks the dirty data but does not actually clean it. Running a view daily and saving it to a new table incurs unnecessary BigQuery costs and operational complexity. Additionally, it does not address the core requirement of automated data quality management. Why option D is perfectly aligned? Cloud data prep offers the most cost-effective, automated, and scalable solution. It directly integrates with BigQuery, requires no infrastructure setup, and provides an intuitive interface for data cleaning. By scheduling a daily job, data quality is consistently maintained without any manual intervention or high operational costs. Question 253. For this question, refer to the TerramEarth case study. Considering the technical requirements, how should you reduce the unplanned vehicle downtime in GCP? A. Use BigQuery as the data warehouse. Connect all vehicles to the network and stream data into BigQuery using Cloud Pub Sub and Cloud Data Flow. Use Google Data Studio for analysis and reporting. B. Use BigQuery as the data warehouse. Connect all vehicles to the network and upload zip files to a multi-regional cloud storage bucket using gcloud. Use Google Data Studio for analysis and reporting. C. Use Cloud Dataproc Hive as the data warehouse. Upload zip files to a multi-regional cloud storage bucket. Upload this data into BigQuery using gcloud. Use Google Data Studio for analysis and reporting. D. Use Cloud Dataproc Hive as the data warehouse. Directly stream data into partitioned Hive tables. Use Pig scripts to analyze data. The best answer is option A. Using BigQuery as the data warehouse with Cloud Pub Sub and Cloud Data Flow to stream data directly into BigQuery is the optimal solution. This approach ensures real-time data ingestion and analysis, which aligns with the goal of reducing unplanned vehicle downtime. Streaming data enables immediate insights into vehicle health, allowing predictive maintenance models to alert for potential issues before they escalate. Google Data Studio provides an effective reporting and visualization tool to help operational teams track key metrics. Option B is not ideal because uploading zip files to cloud storage introduces delays in data availability. This batch process limits the ability to respond quickly to vehicle issues, which is critical for minimizing downtime. Option C is also not the best choice because using Cloud Dataproc Hive as the data warehouse is less efficient for this use case. BigQuery offers faster querying capabilities with simpler setup and maintenance. Additionally, uploading data via gcloud adds unnecessary manual steps, reducing automation. Option D is unsuitable because using Cloud Dataproc Hive with Pig scripts is outdated for modern data engineering practices. This approach is less scalable, requires more maintenance, and lacks the performance benefits of BigQuery for real-time analytics. In conclusion, option A is the best choice because it offers a robust, scalable, and automated solution that aligns with TerramEarth's technical requirements for reducing unplanned vehicle downtime. Question 254. For this question, refer to the TerramEarth case study. You are asked to design a new architecture for the ingestion of the data of the 200,000 vehicles that are connected to a cellular network. You want to follow Google recommended practices. Considering the technical requirements, which components should you use for the ingestion of the data? A. Google Kubernetes Engine with an SSL ingress. B. Cloud IoT Core with public-private key pairs. C. Compute engine with project-wide SSH keys. D. Compute engine with specific SSH keys. The best answer is option B. Using Cloud IoT Core with public-private key pairs aligns with Google recommended practices for securely ingesting data from a large number of connected vehicles. Cloud IoT Core provides a managed service that allows devices to connect securely using MQTT or HTTP, ensuring scalability for 200,000 vehicles. It also supports public-private key authentication, which enhances security by ensuring only authorized devices can send data. Option A is not ideal because Google Kubernetes Engine, GKE, with an SSL ingress is more suited for containerized applications and API-based services rather than large-scale IoT device ingestion. Managing direct connections from 200,000 vehicles to GKE would add unnecessary complexity and operational overhead. Option C and Option D, which involve compute engine with SSH keys, are not suitable. SSH-based access is not a scalable or secure way to manage IoT device connections. SSH is typically used for administrative access, not for continuous data ingestion from a massive fleet of vehicles. In conclusion, Option B is the best choice because Cloud IoT Core provides a secure, scalable, and managed solution specifically designed for IoT data ingestion from a large number of connected devices, fulfilling the technical requirements of TerramEarth. Question 255. For this question, refer to the TerramEarth case study. You have broken down a legacy monolithic application into a few containerized RESTful microservices. You want to run those microservices on Cloud Run. You also want to make sure the services are highly available with low latency to your customers. What should you do? A. Deploy Cloud Run services to multiple availability zones. Create cloud endpoints that point to the services. Create a global HTTP/S load balancing instance and attach the cloud endpoints to its backend. B. Deploy Cloud Run services to multiple regions. Create serverless network endpoint groups pointing to the services. Add the serverless NGs to a backend service that is used by a global HTTP/S load balancing instance. C. Deploy Cloud Run services to multiple regions. In Cloud DNS, create a latency-based DNS name that points to the services. D. Deploy Cloud Run services to multiple availability zones. Create a TCP/IP global load balancer. Add the Cloud Run endpoints to its backend service. The best answer is option B. Deploying Cloud Run services to multiple regions ensures high availability and low latency for customers by placing services closer to users. Using serverless network endpoint groups, NEGs, allows Google Cloud's global HTTP/S load balancer to distribute traffic efficiently across regions. The load balancer automatically routes requests to the nearest available region, reducing latency and improving resilience. Option A is not the best choice because Cloud Run does not operate at the availability zone level, it is a regional service. While cloud endpoints can provide API management, they are not necessary for achieving global load balancing. Option C is not ideal because Cloud DNS latency-based routing lacks the dynamic traffic management provided by Google Cloud's HTTP/S load balancer. It does not handle failover as effectively as a load balancer with serverless NEGs. Option D is incorrect because Cloud Run does not support TCP-based load balancing. Instead, Cloud Run only supports HTTP/S traffic, and using a TCP/IP load balancer is not suitable for RESTful microservices. In conclusion, Option B is the best choice as it follows Google recommended best practices for high availability and low latency by leveraging multi-region Cloud Run deployment with serverless NEGs and a global HTTP/S load balancer. Question 256. For this question, refer to the TerramEarth case study. You are migrating a Linux-based application from your private data center to Google Cloud. The TerramEarth security team sent you several recent Linux vulnerabilities published by Common Vulnerabilities and Exposures, CVE. You need assistance in understanding how these vulnerabilities could impact your migration. What should you do? Choose to A. Open a support case regarding the CVE and chat with the support engineer. B. Read the CVEs from the Google Cloud Status dashboard to understand the impact. C. Read the CVEs from the Google Cloud Platform Security Bulletins to understand the impact. D. Post a question regarding the CVE in Stack Overflow to get an explanation. E. Post a question regarding the CVE in a Google Cloud discussion group to get an explanation. The best answers are option A and option C. Option A. Open a support case regarding the CVE and chat with the support engineer is the best approach when you need direct assistance from Google Cloud experts regarding the CVE. The support engineer can provide detailed insights on how the vulnerability impacts your specific migration and advise on potential remediation steps. This ensures that you receive tailored guidance relevant to your application. Option C. Read the CVEs from the Google Cloud Platform Security Bulletins to understand the impact is the most reliable source of information regarding how Google Cloud services are affected by a particular CVE. The Google Cloud Platform Security Bulletins specifically address vulnerabilities that might impact Google Cloud infrastructure or services, allowing you to assess the security risk to your application. Why other options are incorrect? Option B. Read the CVEs from the Google Cloud Status dashboard is incorrect because the Google Cloud Status dashboard only reports on service outages or disruptions, not on security vulnerabilities or CVEs. It is not intended for security advisory purposes. Option D. Post a question regarding the CVE in Stack Overflow is not ideal because Stack Overflow is a community-driven forum, and answers may not be authoritative or accurate. It is not a recommended practice for resolving critical security vulnerabilities. Option E. Post a question regarding the CVE in a Google Cloud discussion group is also not ideal because discussion groups may not provide prompt or verified responses from security experts. For security vulnerabilities, official support and security bulletins are always recommended. Conclusion: the best options are: Option A. Open a support case. This provides direct expert guidance on how the CVE affects your migration. Option C. Read the GCP security bulletins. This gives authoritative information on how Google Cloud services are affected by the CVE. Question 257. For this question, refer to the TerramEarth case study. TerramEarth has a legacy web application that you cannot migrate to cloud. However, you still want to build a cloud-native way to monitor the application. If the application goes down, you want the URL to point to a "site is unavailable" page as soon as possible. You also want your OPS team to receive a notification for the issue. You need to build a reliable solution for minimum cost. What should you do? A. Create a scheduled job in Cloud Run to invoke a container every minute. The container will check the application URL. If the application is down, switch the URL to the "site is unavailable" page and notify the OPS team. B. Create a cron job on a compute engine VM that runs every minute. The cron job invokes a Python program to check the application URL. If the application is down, switch the URL to the "site is unavailable" page and notify the OPS team. C. Create a cloud monitoring uptime check to validate the application URL. If it fails, put a message in a pub/sub queue that triggers a cloud function to switch the URL to the "site is unavailable" page and notify the OPS team. D. Use cloud error reporting to check the application URL. If the application is down, switch the URL to the "site is unavailable" page and notify the OPS team. The best answer is option C. Using cloud monitoring uptime checks to monitor the application URL is the most cost-effective, reliable, and cloud-native approach. Cloud monitoring can automatically perform health checks at regular intervals. If the URL becomes unreachable, the uptime check will trigger an alert through pub/sub, allowing a cloud function to execute two tasks. 1. Switch the URL to a "site is unavailable" page by updating the DNS or load balancer. 2. Notify the OPS team using cloud monitoring's notification channels, such as email, SMS, or PagerDuty. Why option C is the best choice? 1. Cloud monitoring uptime checks are designed specifically to monitor the availability of services and trigger alerts if downtime occurs. pub sub plus cloud function is a standard, serverless approach to automate remediation when an issue occurs. 3. It is cost-effective since uptime checks are inexpensive, and cloud functions only execute when triggered. 4. It provides fast response times, ensuring that the site is unavailable page appears quickly after a failure is detected. Why other options are incorrect? Option A. Creating a scheduled job in Cloud Run with a container is inefficient and more expensive. Running a container every minute just to check URL status incurs unnecessary costs. Additionally, Cloud Run does not inherently monitor web application uptime as efficiently as cloud monitoring. Option B. Using a cron job on Compute Engine VM is inefficient and costly. You would have to maintain a virtual machine 24/7 just for uptime checks, which contradicts the goal of a cloud-native and cost-effective solution. Managing cron jobs on AVM also introduces operational overhead. Option D. Cloud error reporting is used for detecting application errors, such as unhandled exceptions or crashes, not for monitoring URL uptime. It cannot switch the URL to a site is unavailable page or notify the OPS team based on URL failures. Question 258. For this question, refer to the TerramEarth case study. You are building a microservice-based application for TerramEarth. The application is based on Docker containers. You want to follow Google recommended practices to build the application continuously and store the build artifacts. What should you do? A. Configure a trigger in Cloud Build for new source changes. Invoke Cloud Build to build container images for each microservice, and tag them using the code commit hash. Push the images to the container registry. B. Configure a trigger in Cloud Build for new source changes. The trigger invokes build jobs and build container images for the microservices. Tag the images with a version number, and push them to cloud storage. C. Create a scheduler job to check the repo every minute. For any new change, invoke Cloud Build to build container images for the microservices. Tag the images using the current timestamp, and push them to the container registry. D. Configure a trigger in Cloud Build for new source changes. Invoke Cloud Build to build one container image, and tag the image with the label latest. Push the image to the container registry. The best answer is option A. Using Cloud Build triggers for new source changes ensures an automated and continuous integration (CI) pipeline for building microservices. Cloud Build will build Docker container images for each microservice and tag them using the code commit hash. Storing these images in container registry, now artifact registry, aligns with Google recommended best practices for managing container artifacts. Why option A is correct? 1. Cloud Build triggers on source changes automate the build process without manual intervention. 2. Building container images for each microservice separately follows microservices' best practices. 3. Tagging images with the commit hash ensures versioning and traceability, making rollbacks and debugging easier. 4. Pushing images to container registry is the best practice for storing and managing container artifacts. Why other options are incorrect? Option B. Storing container images in cloud storage instead of container registry is not a best practice. Cloud storage is not optimized for storing and managing container images, while container registry provides better integration with Kubernetes and other deployment tools. Option C. Using Cloud Scheduler to poll the repository every minute is inefficient and unnecessary. Cloud Build has native triggers that detect source changes immediately, making this approach redundant and less efficient. Option D. Tagging the container image as latest is not recommended for production environments. This approach lacks version control, making it difficult to track changes or roll back to previous versions if needed. Question 259. For this question, refer to the TerramEarth case study. TerramEarth has about 1 petabyte (PB) of vehicle testing data in a private data center. You want to move the data to cloud storage for your machine learning team. Currently, a 1 gigabit per second interconnect link is available for you. The machine learning team wants to start using the data in a month. What should you do? A. Request transfer appliances from Google Cloud, export the data to appliances, and return the appliances to Google Cloud. B. Configure the storage transfer service from Google Cloud to send the data from your data center to cloud storage. C. Make sure there are no other users consuming the 1 gigabit per second link, and use multi-thread transfer to upload the data to cloud storage. D. Export files to an encrypted USB device, send the device to Google Cloud, and request an import of the data to cloud storage. The best answer is option A. Using transfer appliances from Google Cloud is the most efficient, reliable, and recommended approach for transferring 1 petabyte (PB) of data from a private data center to cloud storage within a month. Transfer appliances are designed specifically for large-scale data migrations where network bandwidth is insufficient or the transfer timeline is tight. Why option A is correct? 1 large data volume. Moving 1 PB of data over a 1 gigabit per second link would take several months, even if the link was fully dedicated to the transfer. Using transfer appliances significantly reduces the time to move large data sets. 2. Fast data ingestion. Transfer appliances allow you to export the data quickly, physically ship the device to Google Cloud, and have it uploaded directly to cloud storage. 3. Security. The data is encrypted before transit and decrypted only once it reaches cloud storage, ensuring data security. Why other options are incorrect? Option B. Storage transfer service is designed for transferring data between cloud storage providers, like AWS to GCS, or for transferring data from HTTP/FTP servers. It is not suitable for on-premise large-scale data migration like 1 PB from a data center. Option C. Even if the 1 gigabit per second link was fully dedicated, the transfer would still take around 97 days, which exceeds the 1-month requirement. Additionally, multi-thread transfer won't significantly reduce the transfer time due to network bandwidth limitations. Option D. Sending an encrypted USB device is neither a Google-recommended practice nor scalable for 1 PB of data. Moreover, Google Cloud does not support data import through USB devices, making this option entirely invalid. Question 260. The Dress4Win security team has disabled external SSH access into production virtual machines, VMs, on Google Cloud Platform, GCP. The operations team needs to remotely manage the VMs, build and push Docker containers, and manage Google Cloud storage objects. What can they do? A. Grant the operations engineer access to use Google Cloud Shell. B. Configure a VPN connection to GCP to allow SSH access to the cloud VMs. C. Develop a new access request process that grants temporary SSH access to cloud VMs when an operations engineer needs to perform a task. D. Have the development team build an API service that allows the operations team to execute specific remote procedure calls to accomplish their tasks. The best answer is option A. Granting the operations engineer access to use Google Cloud Shell is the best and most secure approach to manage Google Cloud VMs, build and push Docker containers, and manage cloud storage objects without exposing SSH access to production VMs. Cloud Shell provides a built-in terminal that runs in Google Cloud's infrastructure, allowing full administrative control over resources through the gCloud CLI, without requiring direct SSH access. Why option A is correct? No external SSH access required. Since the security team has disabled external SSH access, using Cloud Shell allows engineers to manage resources without opening SSH ports or modifying firewall rules. Full control via Cloud Shell. Cloud Shell runs on a temporary compute engine instance in GCP and has full access to manage VM instances using gCloud Compute Instances commands. Docker containers, by pushing Docker images to Artifact Registry. Cloud storage objects, using gCloud storage commands. Built-in Docker and gCloud CLI, Cloud Shell comes pre-configured with Docker, gCloud CLI, kubectl, and other essential tools, allowing the operations team to perform tasks directly from the cloud infrastructure. Enhanced security. Access to Cloud Shell is authenticated through Google Cloud Console, meaning there is no need for SSH access or manual provisioning of credentials. The environment is ephemeral, ensuring no sensitive data persists beyond the session. Why other options are incorrect? Option B. Configuring a VPN connection to allow SSH access contradicts the security team's policy of disabling external SSH. Moreover, setting up a VPN just to gain SSH access increases complexity, cost, and security risks. Option C, developing an access request process for temporary SSH access is inefficient and impractical. This still violates the no external SSH access policy and adds manual overhead. It does not align with Google Cloud's best practices for secure resource management. Option D, building an API service to execute remote tasks is unnecessary and overcomplicated. It would require development, maintenance, and security hardening. Additionally, the API may still need some underlying infrastructure, like a VM or Cloud Run, to function, contradicting the goal of avoiding direct SSH access.